So now let's look at an example problem, kind of dealing with this roller coaster. So let's say we start up here, and this is just a model roller coaster, and we'll say that this thing has a height of 2 meters, and then right here it's got a height of 1 meter, and then right here we're going to go ahead and say that's 0 meters high. And what I want to know is, how fast is that roller coaster going at every spot, assuming that it started from rest? So I've got 3 locations: location 1, location 2, location 3. And at location 1, the height is equal to 2 meters. At location 2, the height is equal to 1 meter. And at location 3, the height is equal to 0 meters. At location 1, the velocity is 0. It started at rest. Location 2, I want to know the velocity. Location 3, I want to know the velocity. But this is a frictionless roller coaster, so what I do know is the total energy stays the same. So the kinetic energy plus the potential energy at location 2 is equal to the kinetic energy plus the potential energy at location 1, which is also equal to the kinetic energy plus the potential energy at location 3. Okay, so the total amount stays the same, not the individual amounts. So let's take a look at location 1. If its velocity is 0, then the kinetic energy is equal to 0. The potential energy is equal to mgh. And let's say the mass of this model roller coaster is just 1 kilogram. It makes the math a little easier. So we're going to go with 1 times 9.8 times 2, which is equal to 19.6 joules of potential energy, but it's also 19.6 joules of mechanical energy, because that's the total amount, right? So 19.6 plus 0, that is the total amount of energy of this roller coaster. And since the only thing doing work on it is the conservative force of gravity, that's never going to change. So over here, I know that the kinetic energy plus the potential energy has to equal 19.6 joules. And so I can take 1/2 the mass, 1, times the velocity, v squared, plus mass, 1, times g, 9.8, times h, 1, and set that equal to 19.6. Now this makes sense, right? I've got half of 1, which is half, v squared, equals 19.6, well, minus 9.8, so that's just 9.8. And it makes sense that I'm down to half the amount of energy as I used to have, because half of it is gone as it fell through from potential, and now it's kinetic. So I'm going to multiply by 2 to clear that fraction, times 2 times 2, and I get v squared equals 19.6. So now I have to square root both sides of that and get v is equal to the square root of 19.6, which is right around 4.3 meters per second. At the bottom, we have the same process, except now our height is 0, so our potential energy is 0, which means I can just say my kinetic energy is equal to 19.6 joules, and so I have 1/2 times 1 times v squared is equal to 19.6. Again, I'm going to multiply by 2 to clear that fraction, times 2 times 2, and I get v squared is equal to 39.2, and so square root both sides, and I get v is equal to about 6.3 meters per second. Okay? So the amount of energy didn't change, it just changed between kinetic and potential, and you can see as it got lower, its velocity got higher, and its potential energy decreased as its kinetic energy increased. As it rolls back up the hill, it would do exactly the same thing. We would, or well, opposite I guess, we would gain potential energy and lose kinetic energy as it slowed down and got higher.